There are a couple special types of matrices related to the transpose. So let's define them. Let A be an n by n matrix, so it's square. Then we say matrix A is symmetric. If A equals A transpose. Okay, so let's give you an example, see what that looks like. Consider A equals 1, 3, 4, 3, 2, 7, 4, 7, negative 5. This is a symmetric matrix because if I take the transpose, each row of our first matrix becomes the column of our second matrix. So the first column of the transpose is going to be 1, 3, 4. The second column of the transpose is 3, 2, 7. And the final column of the transpose is the final row of the original, 4, 7, negative 5. Okay, and we can see that the original and the transpose are exactly equal. I get the same thing. Okay, so notice visually what's going on here. We kind of take out the main diagonal. Then the rest of the matrix, that main diagonal acts like a mirror for the rest of the matrix. Okay. The main diagonal is kind of the center of the rotation. If you imagine transposing a matrix is a rotation, you're almost pulling this corner down to this corner and this corner up to this corner. Okay, so if you kind of think about it as a rotation, the main diagonal is the center of the rotation. We have a symmetric matrix when that center of the rotation acts like a mirror. And so we have this kind of reflection across that main diagonal. Okay. One more definition. Again, let A be an n by n matrix. Then we say A is Skew symmetric if A is equal to negative A transpose. Okay, so in this case, let's let A be the matrix 0, 3, 4, negative 3, 0, negative 1, negative 4, 1, 0. If we take the transpose, each row from the original becomes a column in our transpose. So my first column in the transpose is the first row here, 0, 3, 4. The next column is the second row here, negative 3, 0, negative 1. And the final row in A is my final column in A transpose, negative 4, 1, 0. And so we could see these two matrices are not equal, but A is equal to negative A transpose. We just shift by a sign. At every entry, it's the same value but opposite sign. Okay. In this case, the main diagonal kind of acts like an anti-mirror. We still have that mirror behavior across the main diagonal, but now we have to swap a sign too. Okay? Also notice that in order for A to be equal to negative A transpose, because the main diagonal is kind of at the center of the transpose operation, the center of the rotation, each value here stays fixed, right? So 0 stayed 0, this 0 stayed this 0, this 0 stayed this 0. So if we are going to flip signs, in order to do that, along the main diagonal, it has to be 0. Otherwise, if it was something else, if it was like 7, then over here it would be negative 7, right? And I can't change this 7 to a negative 7 by just transposing it. In the transpose, this would have to stay a 7, right? The only number that I can swap signs and have it stay the same is 0. 0 and negative 0 are the same thing. So for a skew symmetric matrix, that main diagonal has to be zeros.